So, hi everyone. My name's Alex Blewitt. Some of you may have seen me around in the past. And on previous EclipseCons, I gave a presentation called Optimizing Eclipse Plug-ins. This was a few years ago because I had been put out of action. But a number of things have changed since then that I thought it'd be worth redoing a copy of this presentation, updating it for what's happened in the meantime. For example, shortly after I gave the presentation, there was an open source profiler called Async Profiler that was released. Java 11 has been released, and that included Java Flight Recorder for being able to have the data in there. And there was a flame graph view that was added to Java Mission Control, which is the viewer for flight recorder events. And of course, there have been many performance bugs fixed in the meantime. So what I'm going to talk about is really the 3 Ds. Diagnose, how to find where performance problems lie. Defer, be able to reduce computation or I/O, especially on the main thread. And then declarative services. If you migrate to declarative services, you can improve the speed of your plugins. So diagnose then. What kind of problems are we looking for? The kind of things that might slow down an application are loading or doing unnecessary work on the main thread. And this could be either resources like images, or it could be classes that you're instantiating or other resource files. It's possible for applications to slow down if there's DNS involved. So when you're comparing URLs, for example, you can do DNS resolutions inadvertently. Or if you're just loading files either repeatedly or that take a significant amount of time from disk as well. So what kind of tools are there to be able to find them? Well, JCMD is a standalone tool that comes with a JOE that will allow you to be able to talk with a running JVM and get some kind of stats out of it. And there's also running Java with the -xlog command to see what is happening in the JVM itself. But there's a couple of others that are worth talking about. Async Profiler, which was released a few years ago, and Java Flight Recorder, which is now standard in Java 11. So what happens when you start an application is that it's going to load a bunch of classes from disk, but there's really 2 different types of loading. There's loading, actually getting the bytes off disk and materializing them in memory, and then initialization of the class. There's resolution and linking as well, but we can kind of gloss over those points. The point is that when you have a class that's defined, you load a bunch of bytes from disk, typically from within inside a jar file, and then store that in memory somewhere. But it's only when you actually start to use the functionality of the class that you'll end up running the CL init, the class initializer, or the static blocks that you might have inside. That's the thing that sets up the values of static fields and any other arrays or top-level content that you have. If you have classes that are referred to within that class file, loading one class may then trigger the resolution of others as well. And in particular, if you're using java-lang method to be able to reflect over methods in a class, then that will cause all of the classes that are mentioned either in return types or as argument parameters or as annotations to be loaded. And so one of the things that you need to be aware of when using declarative services for having dynamic start events is that it will use reflection to be able to find out where these classes are coming from. You can see what's happening by either using -xlog class, that will print out all of the messages that come out. And you can have class star as well, which then adds class star equals debug, which then adds further information. And they're kind of equivalent to passing -verbose class in there. You can also, if you've got a JVM that's running and you want to know what classes there are, use JCMD. JCMD will attach to the process either by passing the process identifier or the application name, and then you can send it other commands. You can do things like perform full GCs, you can get a class histogram which shows you how many instances of particular classes that you have, or you can use GC class stats. Both the class histogram and class stats are fairly heavyweight operations, so it's not something that you necessarily want to do on a live production server, but there are reasonable ways of finding out what your applications are doing. We saw in previous versions of Eclipse, there were actually DNS resolutions that happened as part of a bundle startup. Sometimes these can be completely innocuous because you don't even know that they're happening. For example, if you compare 2 URLs using equals, then that delegates to a URL stream handler host equals. And if you specify host part in the URL, it will actually do a DNS resolution and then compare IP addresses. In this day and age, it's insane implementation. However, it's how Java has always worked, and Java typically is some language that doesn't have backwards compatibility problems. So you could run this in debug point, and I've done this in the past in Java. If you put a breakpoint in inet address get all by name, you can then find out where it's coming from. But running in debug is slow, and it is slightly tedious to find it each time and add breakpoints. Instead, one of the things that Async Profiler allows you to do is find out where you have uses of a particular method. Async Profiler can either load in as an agent at startup, so that you do profiling right from the start, or you can connect it on the fly to an agent that's running, to an application that's running on your server. And the way that it exports events is through a circular ring buffer. So when it's generating events, it writes them to a ring buffer as they happen, and then that contents of the ring buffer is then persisted to disk afterwards in a fairly similar way to how the JFR implementation works. The nice thing about Async Profiler is that recently it's gained the ability to have a built-in flame graph support. So you don't even need to have any other tools. You can just output the content directly to an SVG file. And it's got different event types that you can use. So you can look at what the CPU time happens to be, what the allocations that the applications are doing, what lock contentions there are, and so on. If you're running on Linux, you can also use Linux perf events for finding out what's going on. But importantly, you can instrument single Java methods. So in order to run Async Profiler, we've got Java JVM command with a -agent path. And this agent path then points to the lib Async Profiler dynamic library. Equal start means get it going right from the get-go. And then there are other options that you can pass in that are comma-separated key equals value pairs. In this case, we're writing it out to a text file. And we are then looking for all references that hit the getAllByAname class. What that will do is that will generate us a text file, and it will give you a stack trace for each time that getAllByAname address calls, so you can see not only when it happened, but also where it happened from. If you wanted to, you can do the same thing by passing out a file name that ends in .svg. If you write that, it will assume that you want to write out a flame graph, and it will write that out for you instead. In this particular case, we're looking for calls to new integer, but we're excluding the ones that have value of, because value of, if it's not in the lookup, will call new integer inside there. Actually, I did this just as a test yesterday, and I discovered that there was a couple of issues where we hadn't fixed some of those, so I raised a bug and provided a patch for that. Async Profile can also be used to connect to a running application, and it will run using a Java attach mechanism. So there's a profiler script, which is in effect a mechanism for just running Java with an attach call on there and some translations to pass in the commands to the profiler. In this particular case, we're capturing CPU utilization for 10 seconds. We're summarizing the threads independently, so you see them on a thread-by-thread basis, and then we're writing out the flame graph summary to out.svg. And you can also pass in the example name as reported by JPS. So when you run JPS, it will show you what Java commands are running on your machine. They will typically be the fully qualified name of the main class that you started on there. That doesn't work at the moment on macOS. I've raised an issue and provided a fix for that. So that should be something that we can do in the future. Now, ideally, it would be great if you could right-click on a Java program and then just run it with Profile in the same way that you can do launchers run or launchers debug. So I've had a bug raised that it would be nice if in JDT we had a mechanism to be able to do this without having to remember the complex arguments that you need to put in the VM args. It's not too dissimilar for Java Flight Recorder. One of the advantages of JFR is that it's bundled with Java 11 onwards, so you don't need any other software to be able to run it. You can capture recordings to JFR files. So if you're running this on a production server, you can get some data and then get the JFR file off for later analysis elsewhere. It's got lower head for use in production systems. However, it's a little bit complex to configure. It requires you creating an XML profile if you don't want to use one of the standard types. And although it's very flexible, it's not as easy to configure and trigger just from the command line. And it can be a little bit confusing to understand as well. Finally, JMC was part of OpenJDK 8. That was when JFR was a commercial technology, but OpenJDK 11 no longer ships JMC as part of the standard JDK build. However, you can download it from Adopt OpenJDK, or you can go to the OpenJDK/JMC GitHub repository where there are links to download packages. Like Async Profiler, JFR can talk to an existing Java application, or it can be run from startup. You can specify a couple of default settings called default.jfc or profile.jfc. Those are located in your JRE home directory and lib/JFR, or you can construct your own XML file. And you can either do that by editing the XML file that's provided there, or you can use JMC's template editor, which will allow you to create a custom dropdown of what thresholds you want to set for particular files. The nice thing about JFR is that you can actually customize it with thresholds. So for example, if you wanted to find out where the slow files are, by default, it will look for file accesses that take 10 milliseconds or 10 milliseconds or longer. If you want to see exactly where you're spending time, you can then drop that down to 1 millisecond or even below. So the way we start this is by passing an XX start flight recording option. We've got the file name that we're writing out to in the JFR format. Dump on exit simply means that when the JVM terminates, it's going to write out any flush buffers that it needs to. You can have a duration, which says run for 60 seconds and then stop. And that's useful perhaps if you're connecting to an existing machine. You just want to run it for a certain period of time before disconnecting. And then the settings, which is either the default or profile that comes with the JVM itself, or a fully qualified path to another JFC file that you've written. When you load up a JFC file into Java Mission Control, you end up with an Eclipse-based workspace that looks like this. It's got a bunch of things down in the outline on the left-hand side, so you can step between threads, and inside the threads, you can then see what they're doing. Inside here, we've got a main thread, and we've got a start level Equinox thread, and you can see the little gray section in the top diagram is actually where that was paused, and the execution was taken over and run in the Equinox start level instead. So you can get an idea of where the busy points are and where the locks are within your application just by looking at what quantity of events were captured from there. There's the File I/O tab, and in this particular case, I ran it with a setting to find out a minimum value of 0 milliseconds. So effectively, it captured all File I/O events inside there. And you can track them with stack traces as well. So if you have a look inside here, we've got a couple of accesses to just plug in jar files that are all being loaded at startup, and you can see that we're actually repeatedly loading individual classes from the jar files when they're starting, and it gives you the amount of time it took for each one of those. Now, a new addition to JMC since I last talked about it was the creation of flame graphs within JMC itself. And so if you're profiling an application by using the profile JFC, then you can look in the method profiling and see what the content are. In this particular case, we've highlighted the top packages inside, and we've got a flame graph view that shows at the bottom where it's spending most of those times. If you can't find where the flame graphs are because they're not shown by default, you can go into Windows Show View, and then you'll find flame graph inside there. But the flame graphs are also useful for showing where memory is used as well. If you want to find out where you're generating lots of a particular type of object, you can have a look at the memory analyzer. And again, it will then capture where these classes are being created inside your program, in case it's not obvious where you should look. But I think the most interesting thing about JFR is that you can raise custom events inside there. Previously, it was something that wasn't standardized, and so you couldn't depend on it for providing applications. But now there's a JDK.jfr module, which has the necessary classes to be able to let you create custom events. At the moment, they're all classes. It's highly likely that they are going to be something that you could use for records in the future. In addition to being able to generate events, there's a standard API for being able to process events in the jdk.jfr.consumer package as well. So you can actually automate JFR recordings and then do automated analysis afterwards of what's happening. Here's an example of how we might create a custom event. Let's say we've got a presentation rating. At the end of this, there's a URL, an EclipseCon +1 or -1 that you want to be able to rate on that. We can provide a static method rate event that takes these two parameters. We can create an instance of the event class, and simply by filling in the details and then doing commit, we've written a log to file. The fact that we're calling should commit on there is because it allows you to do a dynamic test as to whether or not this happens. And so you can either enable or disable certain classes of events when you run the JVM itself. And in particular, you can set thresholds. So in this particular case, if you only wanted to capture the -1 ratings because you want to find out how those are, you could then put in a test to ensure that you're capturing at a threshold of 0 or below. If you want to have something that's timed and not just a single shot event, you can then do a begin on the event and then followed by a commit afterwards. So in this case, if we wanted to time how long the presentation happened, we would create an instance of the event class, fill in the details that we need, either at the end or before we commit, and then do begin. What begin does is it captures the current time and then stores that in the event itself. And then subsequently, after you've done your operation, in this case, we're running our deck, it will then do a commit, and that will then record the end time as well. And from that, you can then do a filter to find out how long things took or organize them appropriately. In this particular case, I used it to measure how the Bundle-Activator startup time works, and I blogged about it at the time, 2016. I've updated it now for Java 11 if you want to find out what's happening inside there, and I've got the links both to the GitHub repository that provides it and also the blog post as well. In this particular case, I did an analysis of the Eclipse SDK from last night, and it was about 1 second on my machine. So about half of it is set up in the outside of the Equinox code, and then half of it is setting up the Equinox registry in the update configurator. Of course, starting up Eclipse isn't that fast for all packages, and that's because we've been working to reduce the time spent in some of the other bundles that get started up as well. So that's how we can measure where things are going. But what approaches can we use to make our applications run faster? Well, the fastest way of doing things is simply to not do the work. Right? If you don't need to do the work at a particular time, then delay it until a later stage. So for example, if you've got a bunch of classes that you don't need, don't load them until the first time it's called. If you've got images that you're going to display, then there's no need to get them loaded ahead of time until they're actually called to be displayed on screen. And if you have activators and they're doing an aggressive amount of work inside there, then that can slow down the startup of Eclipse. And it's one thing to say that your libraries assume the existence of this having one first of all, but there's no real reason why that needs to be tied into an activator. It could easily be something as simple as an instance initializer in a class that gets initialized on demand the first time you used it, or some other kind of lazy class mechanism. And it's really a trade-off. Do you want to have everything out of the box to start off fast and have amortized costs, or do you want to spend longer at startup and then have everything instant when it's there? Some of the work we've been doing to fix this, when you look up images from within SWT, you have what's called a descriptor, and that descriptor is really a pointer to data that can then be materialized and shown on screen at a later stage. A URL descriptor allows you to say, here's a URL that we'll want to load the image from, but it doesn't actually load the data until the image is shown on screen. The majority of Eclipse icons use URL descriptor for being able to find it, because bundle entry is a URL schema that you can load content from. However, if you are using something like file locator to find a URL from within inside a bundle and then scanning it by expanding things like the language or the OS that's being used, then there'll be a lot of file IO hitting the jars to be able to find out if one of these things exists with an expanded form. Instead, we've created something called createFromURL Supplier that allows you to pass a lambda in that will calculate the URL on demand. So this is the old way a debug UI plugin used to be able to create its images. We would have something where it would pull on the image, the empty image first of all, and it would do that every time. We then look up the bundle that we were doing from, in this case using platform get bundle. We then use the file locator to be able to find a URL. And actually this was the expensive bit because it was hitting the URL, it was hitting the bundles on disk, trying to find multiple variants until it found it. And then lastly, we pass it into the image descriptor. We've changed this to use a mechanism that allows you to pass in a lambda that will calculate the URL on demand. And so in the same way that the URL descriptor prevented you from loading the bytes from disk in the first place, the URL supplier allows you to not even calculate the URL until you need it. In this case, the file locator that we're being passed in is something that will look up the URL from a particular bundle. And it is essentially a supplier URL. So supplier is one of the Java util functions that came in Java 11 or before in Java functions. And it's something that when you call it will produce a URL. So in this case, we're using something that will pass in a lambda and be calculated on demand. However, you could imagine this being a method reference or other means to be able to provide the URLs for you. The true argument for the create from URL supplier is really an indication to say, if you don't find it, what happens? So if you don't find the image, you get either the missing image descriptor, like the one above, and that's if it's true. And if it's false and it can't find it, then it will return null. So depending on what you want to do with your application, you can then have that as a variant. And just a coding point, if you've got an API where you need to take a lambda, if you have that lambda at the back of the method call, then it allows you to have lambdas that span multiple lines without breaking the flow of code. It's not something that is mandatory or that you have to do, but just as a coding technique, if you have a lambda or supplier as the last argument, then it makes it easy to be. The other thing I wanted to pull out from this is we're using framework util get bundle to do the lookup. You'll find a lot of original Eclipse code using platform.get bundle to take a string and then provide you the bundle class, but that actually has to go through a lookup process to be able to resolve it. If you use framework util get bundle and you pass in a class image, it's really just a couple of steps away because the class has an associated class loader and the class loader is pretty much the same as the bundle. So if you see instances of platform.getBundle, then look at changing them to framework-util.getBundle. If you want, you can have a look at the bug for this, and all of the bugs in this presentation are clickable, so that when you get it, you can find out that history behind them. We've also created something called a service caller, and a service caller is something where you have a single-shot use case for being able to look up a service. In this particular case, we've got an example showing you're doing a call once. So what that's saying is, if I do a call, I'm coming from my class.class, I need an instance of ilog.class, and then I have a lambda which takes that and then passes it into my execution itself. And that's using consumer T, which is one of the other Java User functional things. The nice thing about Service Caller is that it completely abstracts the lookup mechanism. You don't have to worry about what you use it for, and you're guaranteed that when you have that logger, you can then use it for the duration of your function, then afterwards it's going to be returned. You can see the implementation and threads behind that with that bug as well. And I've got a blog down at the bottom where I talked about it, and there's a link to the source code if you're interested. You can actually use Service Caller for multiple cases. So if you want something where you need to do a lot of logs, you can create an instance of Service Caller log, and then you can pass in your calling class and the log class or the instance type that you want to be able to talk to. And then you can just do info and do log.call. Now, the reason for mentioning this is that it provides a simple way of migrating from activator heavy code, where all the activator is doing is looking up the logger or the debug options or something, and you can move it to the class where it's actually needed. One other thing to point out, if the service doesn't exist when you try and do the call, effectively it becomes a no-op. So if you do logger.call and there aren't any instances of ilog, then it just won't do anything. There is a Boolean true and false value that call will return, so you can find out when that's happened and you can take appropriate action if you want to. This can be used in debugging. So quite a few plugins have a mechanism for enabling debug mode, where you want to do a lookup to find out if there is if debug is enabled, and then if so, print something out. In a number of cases, this required an activator to get hold of a debugger service to then look up debug code and then find out if that was enabled. Instead, you can use Service Caller to look up the debug options once and then get the Boolean value out from that. In this case, it's a little bit messier because we are running something inside the Lambda. We're then capturing the return result from that Lambda and then installing it into a field inside an array, and then we're using that to initialize the debugging field itself. The reason why we do it like this, though, is because when you load the containing class that's got the do something method in it, it doesn't actually do the lookup of the debug code at that point, because the inner class has a separate lifetime from the outer wrapper class. And in this case, it's only when we call do something that it will then initialize the debugging holder class and assign the debugging field. And then once it's done, it's final. And so whenever you look it up next time, debugging will either always be on or always be off. So the inner class mechanism is a useful way of speeding up lookups that you're going to do multiple times. There's some information in the debug there, but in all honesty, it's better to use the declarative service component and then inject debugging options if you're doing this, because then everything will be handled for you automatically. And that's a nice segue then into declarative services. If you are using a component and you're building up a lot of declarative services inside there, then it can be beneficial to move those into declarative services instead. For example, a number of plugins, when they start, their activator will kick off a number of jobs. The fact that the jobs are created and then potentially scheduled either for immediate execution or execution in the future isn't so much of an issue as the fact that actually just creating that job is going to cause tens and in some cases hundreds of classes to be loaded to be able to pull in. It's much better to have the job being created as a DS component instead, because that job will then be automatically created when your bundle is started, and it will, importantly, automatically stopped when the bundle is stopped. And within the console itself, you can then turn on and off these jobs by enabling and disabling the component. If we wanted to do that, it would look something like this. So we're using the at component annotation, and PDE will then generate a file for us called OSGi inf ds component. We then have an activate method, which is called when the component is started. And in that case, we're just calling a schedule. Optionally, you could call schedule with a delay. And then there's a deactivate method that's called when the bundle or the component is stopped. And you can use that to then send a cancellation method to the job itself. And so there's a number of places that we're looking at within the next release where we can do some optimizations of jobs that are being created in activators and moving them out to DS components instead. One other example of where you can do this is by hooking into a resource change listener. So resource change listeners are subscriptions to events that come out of the workspace whenever the project workspace changes, typically because a build has happened, the user's added a new file or changed a file. And they are very widely used within Eclipse itself. However, to get it, you have to have in your bundle a lookup for the iWorkspace. Once you've got the iWorkspace, you then call the add resource change listener, and clearly there was an execution ordering issue between these two things. If, on the other hand, you create it as a resource change listener and you have an at reference to the workspace, then your component is prevented from being created until there is a workspace there. And as soon as the workspace comes up, you'll then register with it automatically. Importantly, if the workspace goes away, DS will take care of unsubscribing it from you. So actually, if you move your resource change listeners into a component, you actually get a really good way of dealing with things. And in this case, we've got, again, the activate and deactivate method for being able to register and deregister the listeners itself. When you're using something like this, it's usually a good idea to use a method reference. And in general, you should prefer method references than lambdas for being able to do these things. However, we made an additional change in Eclipse 4.16 to allow you to just publish an iResourceChangeListener interface. And so when you have a component that implements that interface, it's automatically going to be published for you. And then a component called the ResourceChangeListener registrar in the resources bundle will notice that and subscribe it to the workspace on your behalf. So you actually only need to provide this and you get your resource change events for free. If you want, you can specify other things in the component to specify the event masks. So event mask 1 will give you pre-change and event mask 2 will give you post-build and so on. Of course, not all is rosy. There have been some floptimisations on the way, also known as pessimizations. One of mine was I removed XML whitespace from the P2 artifacts file, which had some definitive benefits. It shrunk the size of artifacts by XML by 15% and reduced the time to parse the XML by 20%, which was great. But it caused regressions elsewhere. There were a number of classes that reused P2's XML for writing their own XML files that had absolutely nothing to do with P2 in there. And there was a number of code paths that use buffered reader readline to read the XML file. And when all you have is 156K single read line, turns out buffered reader doesn't work so well for that. So that comes up to my recommendations for what you should do next. Firstly, I think you should instrument all of your code that has a dependency on Java 11 Plus to emit JFR events. JFR events will mix in with the existing implementation of JFR, be able to hook you in with class loaders, be able to hook you in with garbage collection, and be able to do everything that you need to be able to do. So get that set up in there to be able to work. You should download and experiment with Async Profiler. There's links in this presentation, and I'll provide those afterwards as well. If you've got activators that are doing a lot of drudgery for looking up services and registering them, then think about moving those activators to declarative service components instead. And I've given you the patterns for jobs and resource change listeners in here. If you've got platform get bundle, then change those to framework util.get bundle instead. And not only it will be more efficient, but it also gets us away from the giant singleton that is platform. And when you're developing bundles, try and minimize the exposure of internal implementation details to others, if necessary, by not exporting the packages, because the more times I've seen internal packages being exported to others has hurt the ability for that bundle or that code to be evolved over time. And finally, avoid processing XML line by line where possible. Java has a built-in Java XML now. You shouldn't need to do anything line by line. And with that, thank you very much. I've got my link for my Twitter handle there and with the presentation. And don't forget to evaluate the sessions. Sign in and vote at EclipseCon.org, pick this presentation, and then choose the voting. Thanks very much. Now, I think I have maybe 1 minute left for questions. Lots of things inside here. One question, Async Profiler Linux only. It works on Linux and Mac OS, but it doesn't work on Windows. Carsten Thomas usually uses YourKit for profiling. How do you think it compares? Look, YourKit is a commercial product and it's got commercial support. I think it's great for being able to do that. And so I wouldn't talk anything down. Async Profiler is really good at just being a command line tool that you can run on servers. I mentioned CPU sampling and the two profilers. Am I aware of any instrumenting profilers that don't simply crash the profile JVM? I haven't seen any crashes inside there, but your mileage may vary. And the last one from Dennis, how does the Async Profiler compare to Visual VM? Visual VM uses a sampling profiler, and it uses an async mechanism for doing the profiling, so it works in a similar way that Async Profiler does. However, Async Profiler also parses native code and not just the Java code. And with that, I think I'm out of time. Thanks a lot.